Imagine you're managing a metropolis of billions of tiny factory workers' microbes, like E. coli or yeast. And your job is to guide every single one of them to produce a complex, high-value product, maybe a therapeutic protein or a specialized chemical. That's really the core engineering challenge of high cell density bioprocessing. And while the initial blueprint, the strain design, the biology itself, is absolutely critical, the real continuous moment-to-moment control lever you have isn't another gene edit. It's all about how and when you feed them.
That's the fundamental pivot the industry's made. Historically, fed batch operation, or FBF, it was a simple, pretty pragmatic workaround for the limitations of, well, batch culture. Batch cultures, they hit their limits almost instantly, either from substrate inhibition, when you front load too much sugar, or just sudden nutrient depletion that stalls the whole process. Fed batch just solved that problem. It lets you get higher biomass and avoid those sudden
So
crashes.
it started out as more of a defensive measure then.
Precisely. But what's so fascinating here is that FBF has evolved so far beyond simple replenishment. It's now viewed as a really sophisticated control framework. It lets you deliberately manipulate the cell's internal machinery. We're talking about things like intracellular flux distributions, the crucial redox balance, energy metabolism, all while operating at a massive production scale. It's a system that's designed to keep the cell in a constantly high-performing yet constrained state.
Okay, let's unpack this. Our mission today is to understand why modern fed batch fermentation is considered a precision metabolic control layer. We want to look at the powerful, dynamic control philosophy that allows engineers to translate a huge reactor-scale decision like just turning a valve to adjust the feed rate into predictable, microscopic cell-scale changes. This dynamic control over trillions of cells, that's really the heart of successful industrial bioprocessing. Our sources are incredibly clear on this. In modern industrial practice, fed batch fermentation isn't just one strategy among many. It is the dominant metabolic control architecture for regulating microbial physiology at scale. And the core of that regulation, it hinges on one simple physical act: adjusting the feed rate. That physical flow into the bioreactor is the primary op, the manipulated variable you use to constrain the specific substrate uptake rate. Engineers call it the cellular eating speed, or TALR.
And by constraining that job load, you're essentially controlling the cell's economic budget. Think of the cell's entire proteome, all its enzymes and proteins, as a workforce. And that workforce can only be partitioned across a fixed number of tasks. Are the cells putting their limited resources into importing more substrate? Or are they dedicating workers to central carbon metabolism, to respiration, to biosynthesis? When you control the rate carbon enters the cell, you indirectly govern where that cell's entire proteome is allocated.
That level of intentional steering must be incredibly difficult to achieve in simpler systems.
It is. In a simple static batch culture, the cell dictates its own tempo until it crashes. In FBF, the engineer is in charge. This is steering that's, well, it's virtually impossible in a classical continuous system, which just aims for a single, unchanging, steady state. FBF gives you the dynamism you need to maximize product formation, not just stability.
And here's where it gets really interesting for me, because FBF truly acts as a functional interface between two vastly different worlds. You've got these massive, multi-thousand-liter reactors with macroscopic variables like feed flow, aeration, agitation. But those variables are dictating these tiny microscopic phenomena, things like enzyme saturation, cofactor recycling, even global transcriptional regulation deep inside the cells. The feed rate is literally the bridge that links the physical flow of liquid to the regulatory circuits of the microbe. So if the ultimate goal is to constrain carbon flux using that feed rate, we need to speak the language of the cell. Most people, when they think of limiting nutrients, they think generally about a culture being substrate limited. But the source material makes a crucial, more useful distinction that really governs whether your process succeeds or fails.
That's the distinction between substrate limitation and metabolic limitation. Substrate limitation is what you want. It refers to conditions where the external substrate concentration is so low that the cell's uptake transporters are simply not saturated. The supply is the bottleneck. In this case, the specific uptake rate, the QI shroud, is entirely controlled by the external supply rate relative to the total biomass present. The cell is, let's say, hungry but well-fed at a measured pace.
And what happens when you cross that line into metabolic limitation?
That is the critical choke point, and it's a disaster zone for productivity. Metabolic limitation happens when, even if the cell could import more substrate, the downstream processes, the internal machinery, like the respiratory chain's ability to handle the flux or the capacity for biosynthesis, they become the true rate-limiting steps. The pipeline is full and the exit is clogged.
And the consequence of that bottleneck is the infamous overflow metabolism. We hear so much about acetate in E. coli bioprocessing. Is it just wasted energy or does it actually hurt the system?
Oh, it actively hurts the system. If you're in a classic high substrate batch culture, the shale in UCC rapidly exceeds the internal processing capacity. Glycolytic flux increases disproportionately, and the excess carbon gets secreted as low-yield byproducts, acetate, lactate, or ethanol. And it's not just carbon loss. Acetate is highly toxic. It lowers the pH inside and outside the cell, forcing the cell to waste massive amounts of energy on just maintenance and detoxification, which further reduces its capacity to make the product you actually want. The entire goal of a properly designed fed batch is to deliberately maintain carbon limitation, staying safely below those metabolic limits.
That brings us right back to our calculated target, the specific substrate uptake rate, measured as grams of substrate consumed per gram of biomass per hour. That is the internal speedometer the engineer is trying to set.
And under the desired substrate-limited conditions, where residual carbon is low, we can mathematically approximate T-on quite reliably. It's predominantly determined by the feed rate, F, multiplied by the substrate concentration in that feed, CS feed, and then divided by the total culture volume, V, and the biomass concentration, X. This relationship, T-ox emission, F, TSSV, is what allows the engineer to translate a desired cellular performance metric, T-handle, into an actual physical valve movement in the reactor. It's a beautifully simple translation.
So the reason that approximation holds up is because we've engineered the system so that the residual concentration of sugar is essentially negligible. We're controlling the input, not measuring the output.
Exactly. We're forcing the system to operate under supply control.
Yeah.
And operating T-handles below that overflow threshold, below the saturation point for respiratory enzymes, has two critical downstream effects. First, it ensures the cell's oxygen demand, the oxygen uptake rate, stays within the physical limits of the bioreactor's air supply system, which is defined by the mass transfer coefficient, CLS.
Which is key, because if the cell demands more oxygen than the reactor can physically supply, the whole thing just starves, right?
Precisely. And the second benefit is that the cell avoids having to reallocate its precious resources toward those toxic, low-yield overflow pathways. The E. coli example is textbook. By keeping keels constrained, you sustain high growth in recombinant protein expression with minimal acetate accumulation, a yield that is impossible to maintain if you just dump the same amount of carbon in up front.
This means FBF isn't just about managing logistics. It sounds like FBF is allowing engineers to, write a multi-chapter script, a time-sensitive instruction manual for the cells over the course of the fermentation.
It absolutely is. This is the concept of temporal decoupling. Fed batch enables the separation of the process into distinct physiological phases that would otherwise clash. You can have phase 1, a high but controlled gillars to rapidly build biomass under optimal carbon-limited growth conditions. Then you deliberately transition.
And that transition to phase 2 is where the magic of production happens usually.
It is. In phase 2, you might drastically reduce the tolerance, but more importantly, you often modify nutrient ratios. For example, the carbon to nitrogen or CN balance, and you add inducers for protein expression. The rationale is this. Rapid cell growth, phase 1, requires massive protein synthesis machinery ribosomes, which are highly nitrogen intensive. When you switch to phase 2, you restrict nitrogen slightly and slow the growth rate, forcing the cells to shift resources away from building new growth machinery and toward the energy-intensive process of creating and folding your specific target protein.
So you're steering the factory floor from making more factories to making the product.
That's a perfect analogy, and this demonstrates that fed batch is a trajectory controller of cellular physiological state. It steers the cell along a desired timeline, managing its internal state minute by minute, not just searching for one single optimum point to maximize the final titer.
So if Vienna's Lillers is our desired destination on the cell's metabolic map, how exactly do the engineers get the cell to follow that GPS instruction? The sources outline a neat taxonomy of control strategies, starting with the simplest.
We begin with what are called recipe-based strategies. These are fundamentally open-loop control. They follow a predefined profile, and they do not respond to online measurements or disturbances. The simplest are just constant rate or stepwise feeding.
But the most well-known open-loop method is exponential feeding.
Yes. Exponential feeding is elegantly designed to maintain a target-specific growth rate. The feed rate is continuously increased over time, calculated based on the assumption that biomass is accumulating exponentially and the yield coefficient is constant. It's that formula. F0 will pay. It's powerful because it can keep the growth rate safely below the overflow threshold.
But I imagine the drawback is its fragility. I mean, if my initial inoculum was slightly off, or if the oxygen supply had a minor hiccup, the whole pre-calculated schedule just fails.
Exactly. It's like setting cruise control without knowing if the hill is getting steeper or if your tires are flat. It cannot compensate for batch-to-batch variability, inoculum differences, or any unforeseen disturbances. That fragility forces the process to be highly monitored and often runs slower than its potential maximum.
That vulnerability leads us directly to the more robust and, I imagine, industrially favored approach. Feedback-triggered strategies, which adapt in real time to what the cell is actually doing.
The quintessential example here is DO stack control. This strategy cleverly exploits the culture's metabolism. When the cells are actively consuming substrate, their oxygen demand is high, and the dissolved oxygen, or DO level in the medium, is low. The second the substrate runs out, the cell's oxygen consumption drops dramatically, and the DO level rises. Often it spikes sharply. The system detects that rise exceeding a threshold and automatically triggers or increases the substrate feed.
So the cell is basically telling the engineer, I'm hungry, feed me now.
It's highly adaptive because it responds to the cell's actual metabolic state, not a clock. Similarly, you have consumption stat strategies that use off-gas signals, specifically CO2 evolution or O2 consumption, as real-time proxies for metabolic activity. We have clear data showing that adaptive feeding based on CO2 and large-scale ethanol fermentations increased productivity by about 20% compared to fixed-rate feeding. That's a huge economic win just by listening to the cell.
And finally, the state-of-the-art approach in sophisticated industrial settings would be the hybrid multi-input strategies.
They really combine the best of both worlds. Industry often coordinates multiple simultaneous feeds, carbon, nitrogen, and inducer feeds, like running glycerol and nutrient solutions, alongside an inducer feed in an E. coli process. Hybrid strategies might use a model-based or exponential feed profile as a highly predictable baseline, but then use online feedback from DO, pH, or off-gas signals to drive corrective, real-time adjustments. These can even resemble Nutristat-like approaches, where you are actively maintaining the substrate concentration near a very tight, low set point. You're effectively creating a dynamically adjusted chemostat within the fed batch system. The goal is pinpoint precision.
That's a comprehensive look at the control side, but even with perfect metabolic control, the process inevitably hits physical walls. The source material really emphasizes that industrial fed batch success is constrained not by biology alone, but by inescapable engineering limits imposed by the massive scale.
That's the cold reality of scale-up. The first major trade-off is the oxygen transfer rate, or OTR. High cell density cultures, we're talking 50 to 150 grams per liter of dry cell weight. They demand massive amounts of oxygen. The ability of the reactor to supply that oxygen is defined by the mass transfer coefficient, Octane-Callaway. That's essentially how effectively oxygen bubbles dissolve into the broth.
And this capability gets worse as the culture grows.
Significantly. As biomass concentration increases, so does the broth viscosity, and that thickening sludge actively suppresses the effective dollars. You reach a fundamental engineering trade-off that really dictates the final outcome. Increasing biomass only raises volumetric productivity until the physical oxygen transfer rate can no longer support the cell's basic maintenance and product formation requirements.
That sounds like trying to ventilate a massive stadium full of hyperactive marathon runners using only tiny air vents. The limit isn't how hard the athletes can run, it's the lack of oxygen supply.
Exactly. Beyond that inflection point, simply adding more biomass actually reduces specific productivity because of chronic oxygen limitation and metabolic stress. So optimal design does not chase the highest achievable cell density. It targets a plateau region where productivity is maximized, but stability and robustness are maintained long before the cell density limit is ever reached.
The second related limit, especially in high-density systems, is rheology and mixing. I can only imagine how difficult it is to agitate a tank full of thick, non-Newtonian biological sludge.
It becomes incredibly difficult. High viscosity leads to non-Newtonian behavior. Think of mixing honey or thick yogurt instead of water. That elevated viscosity reduces mixing efficiency at a fixed power input, and the result is the formation of concentration and dissolved oxygen gradients throughout the tank.
So poor mixing means you get localized pockets, some areas with way too much sugar, and some areas with zero oxygen.
Precisely. That is crucial. Poor mixing creates microenvironments with localized substrate accumulation, which triggers localized overflow metabolism and stress responses in just parts of the culture. This is why small-scale lab bench feeding strategies can fail spectacularly at large scales if you ignore the co-design of agitation and aeration. The physical constraints just sabotage the biological strategy.
And the final trade-off mentioned in the source is balances specific productivity versus cell density, Kobe.
Yeah, we consistently see that kilomoles, which is the amount of product 1 gram of cell makes per hour, often declines at very high cell densities.
Yeah.
And that's because of stress, gradients, or resource depletion. Therefore, maximizing the overall space-time yield, how much product you make per volume per time, often involves running at a moderate, manageable cell density where a kilomole is high and stable, rather than trying to push for maximal biomass accumulation that leads to a stressed, less efficient cellular factory. The focus has to be on overall process economics.
So what does this all mean? Advanced fed batch is best understood not as a technical compromise, but as precision metabolic control through deliberate constraint of substrate flux. It's a dynamic, powerful framework that shapes both the cellular behavior, the biology, and the plant-level economics and physical constraints all at the same time.
And by mastering the distinction between metabolic limits and substrate limits, and by choosing the right control architecture, whether it's diostat, exponential feed, or sophisticated hybrid engineers, transform the fermenter from a simple reaction vessel into a tightly regulated predictive engine. They're not just giving the cells food, they are dictating the cell's internal operating tempo to achieve maximum value.
We've established that the ultimate operational limit isn't just biology, it's engineering, specifically heat removal and oxygen transfer, both of which are severely constrained by the physics of scaling up. So think about this economic puzzle. A microbial process relies on highly exothermic respiration for optimal growth. This process must inevitably be scaled up in massive stainless steel tanks. Given the physical constraint that you can only remove heat and supply oxygen so fast and so efficiently, how does the engineer decide the most cost-effective moment to slow down the cell's productivity to prevent overheating or oxygen starvation, even when the cell is biologically capable of growing faster? That calculation, balancing biological potential against physical and economic limitations, that's the core industrial puzzle that the design of the fed batch system is always solving.